Got it. I've come across some stuff that I just haven't seen in textbooks, right? So it's stuff that probably, if you know this stuff deeply, you might have come across it, but possibly if you've seen it, but not gone into it in a lot of detail, there's some facts that maybe you don't know. So this is like a collection of those facts, right? So a collection of things about when you're doing variable selection for the purpose of estimating causal effects, sort of what are the issues that crop up. So by the end of it, I hopefully we'll get to a little bit of the new stuff, but really this is a synthesis of different ways of thinking about this particular problem. So in the sort of CS tradition, this is work with my student, Drew. Drew is a very good student, and you'll be hearing about him in the next couple of years or something. Does really good work. He's from Georgetown. He says he's always going to be a runner and a swimmer, but he doesn't have kids yet. So I don't know. Maybe not. All right. So let me tell the story chronologically. It's sort of how I got interested in this. And there were sort of two different stories going on. So one of them was there's a popular folklore result out there in the econometrics literature that says if you want to estimate a causal effect and you know the true propensity score, the propensity score is the probability of receiving treatment given a set of control variables, you shouldn't use the thing you know, you shouldn't use the true one, you should use the estimated one. You should estimate it even though you actually know. So I was trained as a Bayesian, and that seems crazy to me. And so part of this result was like, what's going on with that result? Why is it true? In what sense is it true? And so another way you can frame it is, if you knew the propensity score, what's the best way to use it? Like if you knew the actual function that told you how likely you were to be treated given a set of covariates, if I told you that function, what should you do with it? Okay. So one version of the story on the far extreme end, based on this asymptotic result about variance, is that you shouldn't. You should just go ahead and just estimate it and use that one. And of course, there's a whole bunch of stuff in between. So that's one version of it. And then the other one, which is sort of a similar puzzle, is that if you have a randomized trial, and so the propensity score is a constant function, or a function that you know, the randomization, should you do a regression adjustment? This is another case where there's sort of folk wisdom out there and people will argue about it. Some people will say, no, you should not do regression adjustment if you're trying to estimate an average treatment effect based on an experiment. You should just take the contrast and you should compute the averages, and that should be your estimate. That also seems weird. So I wanted to get, and these two issues exactly are about this question in some sense of variable selection. And notice that the talk is titled feature selection and not variable selection. And the reason for that is that I'm going to be thinking, if you think about the propensity function as a function of a bunch of covariates, the level sets of that function are features because they're composites of other variables. Okay, so that's kind of the context here. It's like, if you know the propensity function, what do you do with it? For this audience, you guys probably know this. I'm going to go through this really quick and not spend a lot of time. But the reason we have to bother with all of this is that if you have observational data, you only get to see one version of what happened. You don't get to see what would have happened. Okay, so sometimes you'll hear this called counterfactuals. Counterfactuals has become a loaded term because it's a term of art in these fields. And so I like the less overloaded one is subjunctive, right? Like would. What would have happened? And we only get to see if you took the drug, if you took it, and if you didn't take it, we only get to see that. And really, we want to know the discrepancy, the difference. Okay. The idea of statistical control is the idea that we want to come up with a pseudo observation that can stand in for the one that we didn't get to see. And I'm going to take an extreme example of this, and I'm going to encourage you to think about twin studies. Okay, the case of a twin study is we have at least one twin in the room, right? The idea with twin is that you've got somebody that is basically a copy of that other person. And so what do you want to do? You want to give one of the twins medicine, and you want to give the other one the placebo, and you want to do that comparison, right? And the idea is that it's a ceteris paribus argument, like everything that's relevant about those individuals we hope are the same. And so we essentially get to cheat, and we get to see what would have happened in that other world. This is why I will encourage you in this talk to think about control as being more fundamental than randomization. Randomization has this reputation in public health and in some branches of social science as being the gold standard. And you'll see this over and over and over if you read the papers. randomization is the gold standard. It's not. The gold standard is being able to see both things. And in some weird cases, like a twin study, where you think that all the biology is encapsulated in that indicator variable of having a twin pair, that is way better than randomization. And just to convince you of that, would you ever randomize? Say you had a collection of twins. You had 20 pairs of twins, you had 40 people. You would never randomize the treatment assignment among those people. This may seem like a basic point, right? But I think it gets to something fundamental. What would we do? We would want to do some sort of block randomization where we randomize which twin. We make sure that one of the twins always gets the treatment, one of the twins always doesn't get the treatment, and then we randomize among those two. Why do we randomize among those two? Because maybe there's still something different. So birth order is an example. Maybe there's some weird thing that happens where the twin that is born 5 minutes earlier is affected by the drug differently. And if we didn't do that, and we had a design where the firstborn twin got assigned to the treatment arm, we would have the usual confounding bias. So the randomization protects us against things we can't control for, but that's really a poor man's version of doing the control. We would love to do the control, okay? And so the question that we address in this talk is, what is the best way to do control? If you can do control, sort of, what's the best way? This goes by other names, omitted variable bias, Simpson's paradox, working variables, hidden confounders. Like all this stuff is the same idea, and I think you guys understand how confounding works. What I will mention in some of these silly examples, so kale and cholesterol. The problem is, if you just had an observational study, the same people that eat kale also do yoga, and they also run half marathons, and so that doesn't tell you what you need to know. Okay, so normally when we think about this kind of, at least I guess I don't want to speak for everybody, but in my case, when I think about these problems, I sort of think about, so Z in this case is going to be the treatment in this talk, Y is going to be the response, and I think about the variables as being X, okay? And this is important because we're going to get into more complicated graphs, but the basic triangle graph says that this is a graph that shows common cause. Okay, common cause is one, but not the only kind of unobserved confounding that you can have. All right, and understanding the distinction between these various kinds is going to be important when you go to the variable section. So common cause would be, you're a health nut, right? Therefore, you're more likely to eat kale, but it also makes it so your cholesterol is good because there's a bunch of stuff over here on that arrow that is all of your athletic activity and your, you were doing triathlons in Sweden or something. Okay. So what I'm going to do today is I'm going to try to synthesize the three major frameworks for formalizing this notion that I just talked about. So hopefully you guys are with me and not too bored already about this idea of different types of confounding and how we want to work with it. And what's interesting sociologically is that these three frameworks that I'm going to talk about, they don't party together, right? Like the people that learn one framework typically don't cross over very often. And for the last few years, I've been teaching a class where I try to teach the top two in the same class. And so a lot of this work has grown out of my experiences trying to convey the strengths and weaknesses of both kinds. And what we're going to end up finding is that these three frameworks are going to be related to each other in a very particular sense, which is that the causal diagrams are going to make more assumptions than the potential outcomes, which are going to make more assumptions than the structural equation models that econometricians use. Now, when I say more assumptions in an audience like this, that might seem like a bad thing, right? But the more assumptions you make, you can deduce things, right? So from a causal diagram, you can deduce an ideal set of control variables. From a potential outcomes assumption that you might make, conditional unconfoundedness, you can deduce mean conditional unconfoundedness, which is the condition that the econometricians use. So I'm going to just lay this all out and show you that they're. So when people say that they're the same, functionally, that like operationally, they kind of are. They boil down to making the same sorts of assumptions, but they're not. They're like a little bit different. Okay. So this is what it looks like. This is what the potential outcomes framework looks like. I'm hoping most of you have seen at least some version of this. And the key thing here, and why this is such a brilliant invention, and it really is. Technically, once you've seen it, it's nothing. But the whole idea is that those two worlds that we talked about, person getting the drug and the person not getting the drug have an independent existence. So it's kind of weird. It's kind of like it's an ontological position. You're kind of imagining that they actually exist separately. It's two-dimensional in the case of binary treatment. Whoever got the drug or you didn't get the drug. So if you think about things as a bivariate object that you want to learn about, it makes the problem crystal clear. Like you want to learn something about a two-dimensional object and you don't get to see both dimensions simultaneously, you only get to see the shadows. You get to see the shadows that they cast on the margins, okay? The way that framework relates to the observed data is via this nice little gating function where the actually observed treatment, which is Z, dictates which of the two potential outcomes that we get to see. So the superscript here is indicating which of the two different potential outcomes. And the thing that we're going to be interested in this talk is the average treatment effect, which is a difference in expectation between these two potential outcomes. The identifying assumptions that we need in order to estimate that quantity are, we need basically the no interference. And that first condition essentially says that if I got the drug, that doesn't affect the outcome of you. This is violated in a lot of educational studies, right? Like if you give somebody tutoring and I'm best friends with you, my tutoring might actually help your grade, right? That's the sort of thing we want to rule out. So that's one thing. Positivity means that everybody has to have some chance of getting it. That means that there's some people that just never had any chance of ever being treated. We obviously can't even entertain that counterfactual or that possibility. And the one that we're talking about today is the last one, conditional invariance, which is we need it to be the case where it's traditionally argued that the sort of way that we think about this is we want that bivariate object, those potential outcomes, to be as if randomized. We want them to be independent of the treatment assignment, conditional on some experience. Okay. So for the purposes of this talk, assume 1 and 2 are sort of always satisfied. And the question is 3. And in particular, the question is how plausible is that counterfactual or that possibility. And the one that we're talking about today is the last one, conditional on.
It's me on the future of that.
We want that bivariate object. So the way that those conditions work is that they allow us to write down the expected value of the potential outcome as a conditional expectation, which is something we can estimate. Okay, so the right-hand side of that equation, we can learn from data. And under these conditions, it corresponds to the thing that we want. Okay. If you are an aficionado and are committed to the potential outcomes framework, that's it. Like that's where you stop this discussion. This discussion just says, as long as X does that, you're good to go. And the tricky thing is, it's not unique. There are many different X's that may satisfy that adequately. And what I'm interested in is what's the best one. And best is a little bit hard to put your finger on. You have to say what you mean by that. But another version of it that we can also try to articulate is what is the minimal one. So what is the smallest set of X's? So in particular, the problem that I set myself out with was imagine that I have measured a bunch of stuff. And I know that if I had measured all of it, that I would satisfy this. Can I get away with less? And do I want to get away with less? Okay. What I'm not going to go into, and what Drew did, was he did a bunch of finite sampling variance calculations and showed that you don't want to condition on things you don't have to, which I hope seems obvious if you guys have the stats background to sort of like it's like saying that if there's a coefficient that you know is 0, you don't want to try to estimate that in a regression, right? Okay, so in that sense, we want to get rid of that. But the story is more interesting because it turns out there's variables that you don't need to control for in this sense, but if you do, you'll get lower variance, right? So in other words, if you think about variables that we have to control for, we don't have to and shouldn't, we don't have to and should. That's sort of like the trichotomy that we're dealing with, but it's unfortunately not that easy. But that's the basic idea in terms of how we want to break this down. Okay, so that's it for potential outcomes. So now what I'm going to do is I'm going to introduce the causal directed graphs framework, and I'm going to explain to you how it bears on the question of which X's we could use, right? Which X's we possibly could use. Oh, sorry, let me show you some pictures first. So put on your potential outcomes hat and think to yourself, okay, it's bivariate. So this is the thing that I would love to learn about, but I don't get to see the scatter plot ever as a matter of, principle. The universe will not let me. All that I can see are, for some people, I get to see the one margin, right? For some people I get to see the one axis, and for the other people I get to see the other axis. And what I'm showing you here is a picture of confounding. So this is what confounding looks like. What it looks like is that if all the red units, if all the treated units are systematically higher than the green units, then when I go and compute the difference, I'm going to be taking the difference between the two dots, whereas really what I want is actually the center of that distribution overall. How does randomization solve this? Randomization makes sure that this picture never happens because it makes sure that the blue and the green, or sorry, the red and the green dots are scrambled, right? And if the red and the green dots are scrambled, then on average, they're going to give me the actual means that I want of the potential outcomes. Good? Okay, so here's how the causal diagrams are going to come in. So we're actually going to start out with the joint distribution of a bunch of variables, and in particular, we're going to focus on these candidate control variables. And the first thing I want to remind you is that any joint distribution can be factored as a bunch of compositional conditional distributions. Okay, so you can think about chaining these together. So in this case, x1 marginally, x1, x2 given x1, x3 given x1 and x2, and you can keep on going. It's non-unique, okay? So I'm a statistician and I'm irritating with my notation, but these F's are different things, right? So depending on the arguments that they take, there's actually a different distribution in there. And I can do any of these, right? So for whatever permutation of the ordering that there are, I have that many different ways of representing the joint distribution. And for the mathematically inclined, I'm gonna assume that everything here is, everything has a density, basically, or a distribution function, so these all make sense to me. So here's the thing. So once you recognize that, though, there are particular, like having chosen a particular compositional representation, some of the terms might actually drop a variable. And what I mean by that is, let's say that x3, the conditional distribution of x1 given x2 doesn't depend on x1. It only depends on x2. Okay, so that's the same thing as x3 is independent of x1 given x2. x2 contains all the information that you need to render the other things unrelated to each other. Okay. This is just probability. This is sort of like statistics and probability knowledge. But what it's going to allow us to do is it's going to allow us to take a particular representation, a privileged one, and map it to these conditional distributions. So in particular, what we're going to do is that anytime that a variable appears to the right of the conditioning bar, those variables are going to have arrows pointing into that. So so x1, x2 here, they would have arrows pointing into the x3 variables. So if I write down dots on a piece of paper, the nodes in my graph for every one of my variables, and then I'm just going to connect them if they appear in the particular compositional representation. Okay, and in particular, in a case that I have conditional independence like this, I'm not going to draw the line from x1 into x3. Okay, so here's an example. So this particular diagram shows x1 through x4, and then I've got my treatment variable and my response variable, and the joint distribution. Is that on every one of them?
Zoom thing. You can move it up.
There we go. The joint distribution can be written like this. That's what that graph says. Okay, that is not unique. Okay, and what I mean by that is, remember I told you before that I can write joint distributions in any sort of way that I want. So in order to make this causal, we just have to stipulate that that's how we're interpreting this. Okay, so you stipulate that the causal relationships are reflected in this particular way. So x1 is having a causal impact on y, and a causal impact on z, so forth and so on. That then implies this particular factorization of the joint distribution. Okay. So in other words, if you have a compositional distribution that corresponds to a graph, that's not a causal diagram, because you can always write down any joint distribution. You have to just say, you have to stipulate, like, these are the causal relationships. We are then going to use the fact that there exists this representation in order to do the math, to do some math that we need to do. All right, so that's one example, and you can just sort of, I have a number of these that sort of go go through. So let's just talk about these so you can get used to them. So one thing I'm going to argue is that these graphs are really nice for thinking through the sorts of relationships that can come from variables, and for no other reason, they're interesting in that respect. So what does this say? This says that x1 and x2 are common causes of our treatment and our response. So you might imagine that that's something we would want to control for when we're doing a regression. On the other hand, x4, the econometrician would call that exogenous. There's these variables that just have stuff to do with these that's unrelated to anything else. So oftentimes we would suppress these and just not show them in the graph potentially. But we don't want to do that. And what I'm going to argue is that in a case like this, we are obliged to control for those things. And we probably want to control for x4, because x4 is going to give us a reduced variance estimator for our treatment effect. And we do not, if we can help it, want to stratify on x3 because we don't need to, and it's not helping us. So that's that trichotomy that I sort of mentioned before. This is a diagram that I call the box diagram. I use this when I teach this stuff. This is my favorite graph. We'll talk about it a lot here. Why do I like this graph? Because there are many different sets of variables that you can use as a control set that are valid. So all of them definitely works. There are others. And I like it in that there is actually there's no common cause here. So I like this example because in the event that, like me, you used to think about confounding as basically common cause, this graph blows that up and it shows you that actually you don't have to have common cause to have confounding. You can have this thing where this thing causes this and this causes something else and then that causes that, right? But it's not, there's no direct common cause. And we'll get back to that example later. This one's going to be super interesting. If you guys have seen this one, this is called the N diagram, and we'll have a bit to say about that. Okay. So just a little bit of recap here. You have to assume that the causal relationships, like you stipulate that. You say that, and then you write it down, and then that's what it is. Okay. These diagrams are useful even if you don't use causality, and they're useful because they can aid computation in doing, if you're trying to compute conditional distributions. And the whole literature on Bayes networks is that. It has nothing to do with causality. It has everything to do with this relationship between graphs and joint distributions. Okay? But don't get those confused because they're sort of separate. And what we're going to focus on today is they're going to allow us to talk about subsets of variables that are adequate, are sufficient for doing control. Okay, so the way that I want to do that is I want to make a relationship, I want to establish a relationship between these things and potential outcomes. Because we've seen potential outcomes, now we've seen these diagrams, so how do you make them together? So the way we're going to do that is we're going to think about what's called a functional causal model. Sometimes it will be called a structural causal model. I try to avoid the word structural because it means 5 things to 4 different people. But you'll see what I mean by functional in a minute. And the way that we do this is that you can think about a compositional density from a sampling perspective. So you can think about an algorithm that takes that joint density and generates data, right? The inputs of that algorithm are the parent variable values, so the values that you need for the conditional distributions, and an exogenous noise variable. And the exogenous noise variable is going to be playing the role of the stochasticity in the sampling distribution. It's going to be a uniform random number, basically, that you use to complete the picture, right? So you've got the joint distribution, and then you use the exogenous innovations to actually see. Right? Is somebody going to monitor the chat, or is there a? Sorry, ignore. So here's how this works. That's the algorithm, and for any given variable, you can just think about a function that takes in as inputs the values of all of the parents, and then the values of those exogenous noise terms, and spits out a number. Okay, and I think if you're sort of comfortable enough with that, this is how you would write out the potential outcomes in a model like this. You need to know what all the values of the input variables were, and you would need to know the value of the error term. But if you know those 2 things, it's deterministic, and that's what's important. Okay? So there is stochasticity here, but the stochasticity we break into 2 pieces. It's the piece that's described by the joint distribution, which the graph tells us what that is, and then there's the exogenous bit. If we have both of those things, everything's just a function. So that's why it's a functional causal model. Like, you give me the inputs, there's a unique output. So what does that mean? That means that I flip the switch on this, and I flip the switch on this, and if I know the value of this guy, that gives me my potential outcomes. Okay. Now, for those of you that are used to potential outcomes, this might look funny in a particular way. And the reason that it might look funny is that it looks like they have the same error term. And actually, there's nothing that demands potential outcomes have the same error term. So let me just handle that real quick. This is what it would look like. This is what the potential outcome distribution would look like if there were an error term for the response y that was the same no matter what z was. It's still a distribution, actually, and you can't really see it here because it's shown as a scatter plot. But the point is that this is a singular normal in this particular case. Like, it's a distribution that lies on the one-dimensional line in this particular case. And so all the problems we talked about before are still here, right? We want to learn about the difference between this mean and this mean. If we have selection bias, we'll get some points, you know, they're up here, and then we'll get points that are down here, and we'll learn that. We'll do it wrong, right? Like, all of that is still operating in exactly the same way, but it looks weird if you're used to potential outcomes. And it turns out it's fine. Like, that would be one version of it. But the exogenous terms tend to be vector valued. So there's nothing to stop us from thinking about that exact same functional causal model that has different error innovations, and Z switches which one is used, right? And the reason that that works out is that as long as that vector is independent of everything else, everything is still fine. But then we get a picture that looks like this, okay? Here's the thing. We can never know if we are in this situation or in this situation. Why can't we know? Because we never get to see the bivariate object. And the means of this thing and the means of this thing are indistinguishable. And it gets worse, right? Because notice that this one, there's some correlation in there. Some of this correlation is due to unmeasured confounding, that is some other x's, right? But another way to think about it is that these two things can be correlated between themselves. There's nothing to prevent that. And that's fine. Everything still works out. So this is an example of that thing. So even if you've done this, I talk to people that do this particular point and the distinction between these two pictures is something that people typically don't think about. They typically either learn one way, the computer science way, or they learn the potential outcomes way, and think about it that way. And the point is that we can't distinguish between them, and they're both part of the same larger framework, these functional causal models. Okay, with me? Any questions? Keep going? Okay. Okay, so the reason that it works out, the reason the intuition here works is that I'm assuming that the x's that we've observed are exhaustive. Okay? So when I write down this graph, when I write down these graphs, there is an implicit exogenous error pointing into each one of these individually that I just don't draw as on basis, right? The idea is that this is a random variable that has a conditional distribution. So even if I knew this and knew this, there'd be some noise left over. And that's what those epsilons are, right? Nonetheless, that's an assumption, right? Like when I write down a graph and then I say the only thing left over that I have to worry about are these element-wise independent errors. That's what I mean by exhaustive. I have all of the x's, it's complete. We don't need that to do causal inference, right? That's bonkers, because that's saying that we're able to write down every single thing that has any sort of deterministic impact on the system that we're looking at, and that's really far-fetched. So what we would like to do is figure out, on the basis of a putative graph, can I get away with a smaller set of x's that is a subset of the x's that I've seen? And Pearl has done many things in his career, but the one that I have focused on was very impressive, is this algorithm for figuring out, given a graph, which sets of variables will do the trick, okay? And so to present that work, the way that I'm going to explain it is that causal inference from observational data is basically a process of elimination. What you want to do is you want to rule out all of the other things that it could have been, and if it's not those things, then the relationship that you see is a cause, okay? So in the context of the graphs, the way that you want to think about it is imagine the graph that there was no arrow. There was no causal arrow from the treatment to the response. In that case, our Z and Y should look independent at that point. Because if they don't, then you know that they're related in ways that are not treatment, and so it must be something else, right? So what this algorithm does is that it considers the graph with this thing removed, and it says, find me a set of variables that I can condition on that would render y and z independent, conditionally independent in that graph. Okay? There's a couple of subtleties about post-treatment variables and stuff like that. I'm setting some of that aside right now. That's the basic intuition. And obviously in the naive kind of triangle graph that I thought about for many years, like there's just one thing and you just condition on that thing and you've done the trick, right? If it's not in this graph, if it's not this, it must be that, right? So the reason that this is not trivial is basically because of this edge case, this thing called a collider, okay? So this graph is called the M diagram, and it's a very goofy case where marginally, x1 and x3 don't have anything to do with each other, right? So check it out. In this graph, there's no arrows pointing into x1, there's no arrows pointing into x3. They're unrelated. So x1 and x3 are independent of each other. Likewise, this does not have an effect on y, right? Causally, there's no relationship causally between x1 and y, and there's no causal relationship between x3 and z. Okay? So I'm just going to tell you that what that means is that we don't have to condition on anything. Like if this is the world that our data was generated from, we could just do the naive comparison, treated average minus untreated average. That would give us what we want. We don't need to. Okay. The problem is that if we conditioned on x2 because we tried to get fancy, that would actually ruin things for us. And so the textbook example of this, if you've not heard it, is imagine that x1 is athletic ability and x3 is athletic and academic ability. Just imagine that, like in the population, those things are not related, right? Some people are born gifted at sports, and some people are born gifted at academics. Some people are born at both, and some neither. And they're basically independent. But now imagine a college that accepts people only if they're good at least one, right? In order to get into this college, you either need to be a really good athlete, or you need to be a really good scholar, or both, but not neither, right? If you did your study and had a convenience sample from that student population, what you would have is that all of a sudden these variables are strongly dependent. Because if I tell you that somebody is no good at sports, what do you know about them? They're a good student, and vice versa. So you went from independent to very strongly dependent, okay? And what that does is that then makes it so that because these things are related, there is now a channel that information can flow between these. So Pearl was really interested in this example and sort of how to avoid it and how to find it. So the algorithm looks like this, basically. We start with a graph, and we find all of the ways that we can traverse from z to y, okay? Undirected, going through any variable. So in this example, right, what are the paths? We can go that, or we can go that. Okay? You can go upstream of the arrow. So find all of the undirected paths. Along every path, make sure that at least one variable is blocked. Okay? What blocked means is either it is not a collider and you conditioned on it, or it is a collider and you did not condition on it. Okay? And that's it. That's the algorithm. So it's great. What it means is that if we have a graph, there's an algorithm you can run that runs pretty fast. It just enumerates all the paths and it just checks one by one. And what it tells us is that it allows us to find conditioning sets that we can use to do causal inference. Okay? Because there's this equivalence between these diagrams and the potential outcomes, you can see that if I satisfy this condition, I have satisfied conditional decondensance. Okay? It's the same. So let's take this example. So what could I use? So let's say I condition on x3 and x4. That's not good. So conditioning on x3 and x4 means that this path is still open. So that doesn't work. Likewise, I can't just do x1 and x2 because that leaves the bottom path open. X2 and x3, that works. X4 and x1, that works. And then any set of 3 will work, and then all 4 will work. Okay? But I think it's pretty interesting, some of these sets, right? Because that says that I can control for x2 and for x4, and that's cool. That's enough. That's a really weird way to think about it if you're thinking about propensity scores. Because if you sort of think about propensity scores are what variables are dictating the probability that you get treated. And neither of those variables has any direct impact on that. So, these variables are basically adjusting for the level of the response and not the propensity to be treated. Conversely, I can condition on x1 and x2, and that would also be okay. And that's more of how you might think about it if you use propensity scores, because those are the variables that are relevant for dictating how likely somebody is to receive the treatment or not. And then, of course, the sets where you mix and match are interesting, right? You can take some variables that are Y related and some variables that are Z related and mix and match them in various ways and still achieve what you need to achieve.
So, question from your point in the beginning was that there's more. You're making more assumptions here because you lay down this graph to begin with.
Yes.
So by making more assumptions, you're able to get away with a possibly smaller set of.
Yeah. So
it's a question. So the question is that assumption something you'll be able to substitute by some sort of a model selection?
Okay. That's where we're going, right? The idea is to try to use what we know about these graphs to come up with procedures for doing variable selection that acknowledge whatever issues crop up due to a particular graph. So in practice, I don't want to have to assume the graph, but I do want to develop methods and use the graph technology in order to help me develop methods that satisfy certain things. So that's kind of where we're going with this. But to the other point, right? I can make that point now that you can see that this is more assumptions, right? When you just straight up say, I'm going to assume conditional dependence, that just says that whatever x's I'm telling you I have, those x's do the job. This allows you to deduce different sets, but it requires you to say that you know the whole world, right? That you know everything. So it's a stronger assumption, but it allows you to deduce it and find novel things. So it's kind of weird calling one stronger, and one is just assuming the thing that you need to assume and nothing more. The other one is assuming more, but it's trying to be more principled because it's trying to articulate what the actual relationships are. Other than, basically, if you're doing this in a potential outcome framework and you just say x3 and x2 are good to go, right? That leaves a lot to be desired in terms of understanding what the mechanism is by which that has been achieved. And as you can see, there are different ways that can occur. Anyway, this is okay. So that's the algorithm, and it's great. And I already went through this slide. Of course, the collider one is weird, right? Because you don't have to condition on anything. You can condition on all three. What you cannot do is condition on x2 only. Conditioning on x2 only. And if you guys follow any of the stats blogs, there have been some ugly flame wars about this question, and it's a mathematical fact that can happen. The question empirically about whether or not colliders are sort of something to worry about. I think the idea, so I'm going to throw my hat in the ring on this. I think that colliders probably don't happen very often in the sense that they exist in the data set and then you were super dumb and only conditioned on that. I think what's much more likely is what I described before, which is where the sample that you have has already implicitly conditioned on something that has induced relationships between variables that you wouldn't necessarily expect there to be dependence between. So every psychological study ever done that has used college students, right, would potentially run afoul of this. Okay, so now that we have this, what I want to do is I want to tell you sort of the way that I've been thinking about these things, which is once you have the DAG in hand, you can start causal directed acyclic graph. I think I mentioned it, but I didn't say it. Causal directed, so DAG. So basically, arrows that point only into Z, I refer to as instruments. Those of you, that's sort of intuitive if you think about that. Pure prognostic would be the variables that don't have a relation to anything and point only into Y. Common cause is one that has causal arrows going into both. And of course, if there's a variable that's just disconnected, then that's a noise variable. And in practice, we don't know that. So often if you're a bioinformatician and you have measured a bazillion epigenetic locations, a bunch of those probably don't have anything to do with anything. They're there nonetheless, okay? So here's the problem with it. So these designations are helpful for starting to think about, okay, well, what do we need to control on minimally? And what ought we to get better variance? The problem is that they're provisional, right? Because once you realize that there's this dependent structure in the graphs, in a situation like this, conditional on x2, x1 is an instrument. right? So if I'm committed to conditioning on x2, then I don't need to condition on x1, and I shouldn't, statistically speaking. On the other hand, if I have conditioned on x3, x4 is a prognostic variable, and I don't need to. So it's complicated, right? These variables don't have absolute designations as one type or the other. It's all relative to whatever the other conditioning set is that you are already using, which makes the problem of variable selection in this context quite difficult, because it means that, and we know this from linear regression, that when you take something out, it changes the estimates of everything else. But you can see that like moving to nonlinear machine learning type models does not solve this. This is an inherent problem with joint distributions and what happens with conditional independencies as you take things out and put things back in.
It's almost like if you're trying to do variable selection in a graph, then the order of the decomposition matters.
Well, yeah,
right?
Because the order of
That's right.
decomposition doesn't
That's
matter.
right.
Yeah, that's right. And so when you start thinking about this, what the goal is of this work is to try to come up with methods that don't need to know the graph, and nonetheless can find subsets that are smaller than all of them to do our estimation on. The other thing, and this is another one of those nuggets that maybe even if you've worked in this area, you might not have seen this particular example, is that the graphs themselves are non-unique. So they're only unique if you think that the variables that you've measured coordinate-wise are sort of privileged in some particular way. So the example I'm showing you here, so we started out with this graph at the beginning, and I said x1 and x2 are sort of these independent variables from each other that are both common causes, right? But if it turns out that the way that they appear in the functional causal model is that they modulate the treatment and the response based on whether or not they're equal to each other, then it turns out that the indicator variable of them being equal to each other is actually the only relevant common cause. And you can rewrite that graph, you can sort of decompose it into the value of x1, and then conditional on knowing that, w has some distribution, which is basically the independent component due to x2. And so the point is that these two graphs are empirically equivalent. You could never sort of tell them apart. And that gets back to this issue of like variable selection and feature selection are different. Okay, so in terms of variable selection, I have to condition on both of these two things. And just in a simple case with each of these is dichotomous, that means I have to condition on 4 straight. Whereas if I knew additionally that W was actually the operative thing, the only thing I would have to condition on is whether or not they're equal, and that only has 2 straight. So again, whether or not this is sort of practically relevant is a difficult question. I think it's important to be aware of the variable selection and feature selection are a little different, and the graphs are sort of non-unique with respect to those transformations. And by the way, equal is a little bit stylized, but think about ratios, right? Think about body mass index, right? Body mass index is a ratio essentially of mass and height, right? Is it height that's doing it, or is it mass that's doing it, or is it the ratio? Well, if it's the ratio and the height and the weight are basically, if you can decompose them independently, you can exactly get this sort of setup, and you wouldn't know. Okay. So now what we're going to do is we're going to go into the third step, which is additive error models with exogenous errors, which is sort of what the econometricians historically have thought about this. And in order to do that, it's going to be convenient to think about a treatment effect, a reparameterization of the potential outcomes that I am fond of, which is just, if you define the treatment effect as the difference between the 2 potential outcomes, then you can rewrite the Y1 potential outcome as an offset from the treatment effect. And then the unobserved data can be written just by taking the first line was just what we had said before. So this is the standard thing. And then making these substitutions, you can get it into a situation where Z is basically just adding an offset. Now, I have written this here sort of for an individual. Right? So, nonetheless, does this track? I know for some of my colleagues, it definitely does. We use this all the time. But the reason that this is nice is that it allows us to think about those functional causal models in a way that statisticians are particularly used to, which is, remember that these functions are deterministic, and they determine, given the exogenous errors and the particular values of the controls and the treatment assignment, it tells us exactly what we would get, right? So that is the potential outcome. But thinking about that now as a function, I can now write the treatment effect as a function. Okay, so it's a difference between two other functions. Then, having done that, I can rewrite the observed y, just a reparameterization of the functional causal model. Now, what I like about this is that it makes clear that the confounding can happen essentially in two places. You can have confounding in the sense that these x variables are related to z and this term, or they could be related in that term. Okay? And we have found this very useful in our work to distinguish between these two things. So this would be confounding at the moderation level, that affects the actual gap between the two. And then we call this prognostic confounding, which is confounding that occurs over here. Okay? This is all just symbols, right? This is just taking the formulas and rewriting things in a slightly different way. But what it allows us to do is, now that we've done this, we can take expectations. And in particular, we can take expectations with respect to those innovations, because those are the exogenous errors in here. And that can give us a representation for the mean structure of the model. And now, just these equal signs should really be definitions, right? But we're saying take the expected value over those stochastic terms that are exogenous, and that gives me a mean function for the structural model, the functional causal model. I can do the same thing with the y1 potential outcome, take that expectation. By the way, this error here does not need to be additive. So notice that, like here, that's showing up in this function. And so when I take this expectation, this thing can look nothing like like this. Like weird things can happen when you take an independent error and you pump it through a nonlinear function, right? It's not going to decompose particularly. Nonetheless, we can define this and this as those expectations. Then, once you have the mean, you can essentially centralize things. You can take the actual potential outcome value and subtract off the mean structure. And likewise, you can take the treatment effect mean and you can subtract off that from the actual treatment effect structure. So let me sit here. Like if you've not seen this before, it's nothing, it's mainly just definitions, right? Like I'm just rewriting things in a way that I can take averages and then I can define the error terms additively, okay? So I'm taking a nonlinear model and I'm making it additive. I'm sucking out the mean structure, and then I'm redefining the error terms as this epsilon and this level. Okay. Here's why that's nice. I can then take those definitions and go back into, plug those back into the framework, and it's just a reparameterization of the same thing. And you can see that I can write it out as y is equal to a model where this thing is essentially the causal mean. If I change x, then the mean causally of that variable will change here. And then there's this error, right? And then there's a treatment effect that'll be an offset from that based on the value of z, and it has an error, okay? This is the most general form of what I would call a structural equation. Not the typical way you see it written, because most of the times this thing is not even there, and this thing doesn't depend on x, but it can. Okay, so what is the key thing about this? The key thing about this is that this is mean 0 for every value of x. And this is mean 0 for every value of x, just by the way that we've defined it. Okay. All right. Are there any questions about that particular? Like, if I don't want to go to the next slide, if there's like extreme confusion about what that is doing. So we've stepped through, right? We started with potential outcomes, and we got functional causal models, and then I just took expectations over those functions. And then I redefined things in terms of these error terms, and this is what I get. This is going to be kind of my baseline representation in the way that I work.
Define to me in word the delta of x is it's the noise on the propensity. When you get it.
Yeah, so every individual can respond to the drug in idiosyncratic ways that don't depend on x, and that depends on x and also other stuff, right? Yeah. And by definition, by the way I defined it, tau is the average of that. But people can there. It's a powerful way to think about it, right? Because it really encourages you to think about, oh, hey, there's heterogeneity in units based on the baseline value, and there is also variation in units based on the way that they respond to the treatment. And it's both things, and you need to account for both things somehow, otherwise things go wrong, right? Okay, so that's that. But in practice, what happens, right, is, so notice that in all of these derivations, I've been assuming that x is exhaustive. Okay, so this is my next little nugget. Okay, If X is not exhaustive, these functions are not going to be these functions. Okay, these functions are assuming that this is based on, like when I do the integration here, I'm just integrating over that. And integrating over that, it's exogenous. And what that means is that whatever's left over here in tau and mu is causal. Like I can think about that counterfactually. I can think about if I change the X, the thing moves, right? But imagine that I have a graph like this, and the variables that I start out with are not x1, x2, x3, x4. Let's say that I only start out with x1 and x4. Okay? How would I represent that? So I start out with this particular representation, and now I have to integrate out over that, conditional on x1 and x4. Okay? And what happens is I have to integrate out x2 and x3, given x1 and x4. And so what you can get is like this variable here might only involve, in fact, we know that it only, what does it involve? It involves x2 and x4. How do I know that? Because those are the ones that have causal arrows going into y, and this is the expected value of y, right? So what that means is that if I now have this and this, that means that when I integrate over x2, x1 is going to show up. Because x1 is going to show up because x1 is going to help me predict the value of x2 that I don't get to see. And it actually is fine. It works out fine. And the reason it works out fine is that as long as you have a subset that satisfies the condition of deconfoundedness, then everything's going to work out and it's going to be. And I'm just take my word for that. Like I don't want to go through the details of that. But what I do want to point out is that what it's going to leave you with is it's going to leave you with a model that has these modified functions that are now based on other stuff than what was originally there. And these models are not causal. Okay, what do I mean by that? In this graph, x1 does not causally affect y. So mechanistically, if I modified the value of x1, y would not change, right? It's not causal. But in this model, x1 appears right there. So, you know, when I, as an undergraduate in econ, when I heard about structural equation models, they said, oh, a structural equation model looks like this, and then you've got error terms that are exogenous. I never understood what structural meant, because I was like, structural in what sense? And my guess, and you know, people aren't dumb, like but I think what the deal is, like, they had this in mind. This is structural in the sense that like I can interpret those causally. But what's weird is like you actually don't need that. You don't need it to be a structural model. You just need to have the exogenous error. So again, that's something like I didn't really appreciate that until I had gone through these derivations and seen that. So the next time the econometrician writes down their structural equation model and this thing here looks bonkers, because you're like, why in the world would those things be affecting this thing? They don't have to. It just has to be an association that can be leveraged somehow. And that doesn't really matter. All that matters is that the resulting error terms are related. Okay. And then the last step, how am I doing on time? No idea. It doesn't mean anything. Tell me time left. Okay. So, all right. So where I want to go with this next is I actually want to reduce the conditions even more. So in this particular setup, we still need it to be the case. We're still assuming that the set that I'm using is satisfying conditional deconfoundedness. Okay, so you've given me an S, some subset, and that subset has the property that it satisfies the Perl algorithm, which means that it satisfies the conditional deconfoundedness. If I'm only interested in average treatment effects, I actually do better than that. And so what I want to do is introduce this definition called mean conditional unconfoundedness, which is starting out with that particular representation, and then all that I want is, actually I can find it on the other slide, there it is. So here's what I want. So in the structural version of the model, meaning the version where X is exhaustive, according to the graph, I have this function u and I have this function tau, right? Those are the functions that come from the functional causal model as I defined it on the previous slide. And what I need is I just need to find a subset of S or really it's a function of S, like more generally, right? But I needed to know a subset of the variables that render these two things conditionally. So I don't actually need it to be independent of potential outcomes if I'm only interested in the mean. I just need it to be conditionally independent of the mean potential outcome, which sort of makes sense if you think about it. And this gets you in, you can go down a measure theory rabbit hole with the sigma algebras and stuff involved with this, but it's kind of cool. And this is the proof and shows how it works. And it's a 3-line proof, but the first line here actually doesn't take advantage of the independence at all. This just takes advantage of the fact that these terms are mean 0 for every x. So the first assumption is that because of the way I define that, those terms go away. And then I introduce the conditional deconfoundedness by inserting z there, which I can do because it's independent. And then I just gather out my expectations, and then that becomes what I need to be. And then the proof follows from the fact that this right-hand side is something I can estimate. So what are the implications of this, and sort of how does this shake out? So what this means is that I actually don't even need to worry about these bits in the event that I only care about the mean estimation. And let me just give you a concrete example of how this would work out. It might be the case that there's confounding in the sense that some of the x variables that are affecting z are also affecting the distribution of this thing, the tails, right? It's making it skewed or something like that, or it's making it really high variance or something. What it means is I can't do quantile regression in this context. But if I only care about mean regression, all I need is unconfoundedness on the mean structure of the potential outcomes, that's appealing to me because I've always thought it was bonkers to have to assume independence is a much stronger condition typically than just assuming that you can, if you're estimating a mean, you would want that. And so that's what this condition is. And furthermore, this now takes us back to the econometricians. And now you can see that because of in that context, you really are interested mostly in means, that kind of justifies dropping those terms because those terms they might be skewed or they might be confounded, but as long as they're confounded in higher moments of the distribution, it's not going to matter for mean estimation. So the typical way that you'd see this is this term would just be gone, this term would be gone, and you'd say, assume the conditional on z, the error term that's left over is exogenous. So it's one level, right? We're gradually weakening our assumptions, and so now we weaken it further where we only need this other condition. And by the way, it can be quite a savings in the sense that imagine that the variables that appear here, there's only 3 of them, right? And then but there's a whole bunch of variables in here that affect things about the distribution. We don't actually have to worry about them. Like technically, yes, it's confounded because it's not independent. The distribution changes, but the mean doesn't. So, okay, so that's sort of the take home on that. So, okay, so now once you've started thinking about this, we can come back to the original problem, which is how am I going to use all of this to think about how I can do conditioning sets that are tiny. And this example was really striking to me, and I hope it's striking to you, so I'm going to try to walk you through it slowly. So this is a case where the graph that I have in mind is basically the simple one, okay? But the functions that are involved in terms of dictating the values of y and the propensity are particular, okay, sort of stylized. So in this particular example, x is a discrete variable that can take on 20 values. And the prognostic function, the mu function, so what I'm plotting here is mu and tau, right? So tau is assumed to be constant, and I'm plotting mu and pi, okay, mu and pi. Pi is the probability of receiving treatment, and that's the one that oscillates over to the left and then goes flat, and then the other one is flat and then goes up, okay? I could come up with a story for this. It's actually better if you guys come up with it, but this kind of thing sort of can happen, right? So as a student goes through school, they might gradually be more likely to receive some particular treatment, and then they get to high school or college, and it doesn't go higher than that, or vice versa. Nonetheless, the reason that this is valuable is that I want you to think about what conditioning sets we could use here. And the idea is that if we want to eliminate systematic covariation, one way to do that is to just eliminate covariation. right? So the propensity score does this, right? If we know the propensity function, then all of the randomness is taken out of the z component, and z is like that. The propensity is a constant on every strata of the propensity function. We can also do prognostic control, which is where we know everything that depends on y. And this goes back to this graph, right? This is just saying you can either condition on x1, x3, or you can condition on x2, x4. And either of those approaches are mu is not, and on the regions where mu is varying, pi is not. And so what that kind of tells us is that we should probably be able to get away with something cruder, and indeed we can. The only thing we need to know is whether or not x is greater than or less than 10. So this is just a cute little example, and you can't deduce this actually from a graph because this is not in the graph structure. This is actually in the structure of the pi function and u function of interest. What I'm showing you over here on the right is what you would get if you conditioned on different sets, okay? So the purple one is conditioning on nothing, okay? So this problem is confounded. And the reason that it's confounded is that the average level of pi on the region where mu is varying is different than the average level on the other side. So like if you don't condition on anything, you get some pretty severe biasing, and that's why the purple is not in the right spot. All of the others do fine. And so mu is conditioning only on the black dots, and in particular, the values of the black dots that are unique, right? So the green is conditioning on, I guess, what is it, 11 levels. The pi function is in black. It is conditioning on a different 11. It is conditioning on the 11 where the propensity function is unique. And then the yellow is conditioning on everything. And then the special one, I think it's called lambda, you can't really see it there. That's conditioning on the indicator variable. Is it to the left of 10 or is it to the right of 10? And what you see is that all of them are unbiased, which is what it means to be deconfounded in this context. And but you get gains from not conditioning on stuff that you don't usually condition on. And but the green is only slightly better than the yellow. And the lesson there is like conditioning on more stuff seems to be okay, modulo the collider issue, which is it's real. But this is tricky because basically in order to understand that, in order to do this, you need to know mu and tau and pi, and you don't typically know this, right? But in principle, you do. So the result, which is sort of non-functional, is a sort of oracle result in the sense that it's based on stuff that we can't possibly know, but if we did, this would be the right answer. It turns out that the principal control function is defined the following way. It's the expected value of the propensity function given the prognostic function and the treatment effect function. Okay? So obviously we don't know mu and tau. We're trying to estimate tau. So in that sense, it's not very helpful. But what it does tell us is it tells us that we can actually do better than pi. And so if you think about this, conditioning on mu and tau as opposed to conditioning on x, that's getting rid of noise variables because we took that expectation and those all went away. And then the outer expectation is getting rid of instruments because now we're getting rid of all of the things that pi depends on that don't have anything to do with the mean function of interest. So this is what we call the principal control function. And if you go back to this example, you'll find out that the clever thing that we did is this. Like if you take this definition and apply it to that example, you get back an indicator function that's sort of on that region, which is nice. The definition does the thing that we want to do. I put this up here mainly just to show you that I did it. But the proof for this is the proof for this is similar to the proof that in the propensity score paper, showing that the propensity score is a minimal balancing function. But what's cool about this is that lambda here can be coarser than the propensity function. So there's this. So here's another one of these kind of nuggets. In the literature, because of this really influential paper that said the propensity score was a minimal balancing function, people took that word minimal and took the fact that it was a proof and said, okay, we need to do the propensity function. But it turns out that that balance is on all of x. And in particular, it balances on all of the x's whether or not you need them. And this is saying, no, this thing can be strictly smaller than the propensity function, as the last example just showed you. And it can also be coarser than mu and tau. And in fact, it is the coarsest function. And that's what this proof says. It says basically, like, assume that it wasn't the coarsest function. That means that there's some strata in which these two things differ, and then you get a contradiction. Okay. But it gets weirder, because it turns out that if you apply this definition, this whole definition of minimal is subject to the x's that you started with. Okay, so the way the proof works, at one point you have to say, well, there's that many unique conditional distributions of z given these two things, right? Well, as we saw a few slides ago, those two things are going to change depending on what the set of x's is that you started with. Okay? So this thing is truly minimal in the case that you start out with an exhaustive x. Okay? It works out. But what happens is that it actually does not work out if you start out with a non-exhaustive x. So imagine that you've got the collider graph here, and that you don't get to see x3. Okay? And you don't know any better, but the full control set is x. In that case, let's say we're going to condition on x1 and x2. So we start out with x1 and x2. That's our basic. Okay? And now I say, okay, I want to now minimize that. I want to reduce it. So what happens if you apply the definition, though, is we want to know what is the expected value of pi, which is governing this thing, given the levels of the prognostic and treatment function, which is based on these two things. And here's why it's tricky. When we don't get to see this, but when we condition on this, all of a sudden there's a path that goes from x1 to 1. All right? And what that means is that that mu tilde function that we wrote down, both of these are going to appear there. It's going to look like they matter. Okay? So then when you go to the definition, of the principal control function, you're going to condition on those sets. Okay? So in the most generality, what you end up with is you end up conditioning on x1 and x2, and then you want to find the conditional expectation of z given x1 and x2. So what is it? It depends on z. Z1. Sorry, it depends on x1. So if you condition on x1 and x2, according to this graph, and then you say, of those sets, what does pi depend on? It only depends on x1. So what you end up getting, though, from this graph then is that you end up concluding that the minimal control function is x1. But that's not true, because we know in this case that the minimal control function is actually nothing. You don't have to control on anything. So the trick to it is that you can iterate it, because if you know that if the lambda definition that you get worked, then you can use that as your new conditioning set, and you can apply it to the logic again. So now do it again. So now x1 is our conditioning set, but using only x1, that's actually not related to y anymore at all. And so when we take the expected value with respect to that function is constant, and then we get back to our answer. So that's a little tricky, and honestly, it causes lots of problems, right? Because whatever the thing that you start with, because it might not be exhaustive, might have these weird induced dependencies, so that even when you go to try to define the minimal possible control set, it doesn't give you the minimal possible control set. But the good news is that you can iterate it and eventually just drive it down to the minimum. Okay, so there was one more thing, but at this point, people's eyes are swimming. So let me give 2 pages of summary and go over this and sort of just hit the highlights of what I hope that you sort of took home. Potential outcomes are really important, and they're very, very useful in this idea that they exist separately. And if you can sort of internalize that, it's great. Okay. But causal diagrams have their place, and in particular, they really help clarify the subtleties of conditional deconfoundedness in a way that you just don't get to see if you just say conditional deconfoundedness or propensity score. And you get to see some of these issues when you pay attention to those. Furthermore, the econometrics exogenous error model is actually a minimal assumption. It's actually the more minimal of the 3. It's opaque in the same way that the potential outcomes are, but it also it's less strong than the other things. Control is more fundamental than randomization. I'm just going to throw that in there. I didn't really demonstrate that, but the whole talk is really about that, right? The randomization is sort of the byproduct, sort of where you get. Conditional deconfoundedness is strictly stronger than necessary for estimating ATs. So that's one take home, is that that's the typical starting point that people start at, and it's actually not necessary. You can have confounding, but as long as it's in the tails or the higher normals, like you don't need that. Structural equations don't have to be causal. Like people write down structural equation models, the word structural makes it sound as if they are causal, but they don't have to be. And they work just fine even if they're not. So it's really the exogeneity of the additive error there that's sort of the relevant thing. Knowing the propensity score, and I wasn't able to get into this, but knowing the propensity score can be beneficial if it prevents screening out irrelevant variables. All right. So that result that I alluded to at the beginning was based on the idea that they did an asymptotic variance calculation, and it turns out that you get a reduction if you do some in-sample balancing, basically. But the sort of thought experiment you can do to convince yourself that that's missing part of the picture is imagine that I told you the true propensity function and it only depended on one variable, and the learned version would have had 12 variables or whatever. So at least in that bare context, you would think that like, oh, that unlabeled data is really useful in telling me that I only have to worry about these 3 things and not these dozen things or half dozen things. I'm going to skip that top one. Notions of instrumental and prognostic variables, it's inherently contingent. Right? This idea of what is necessary to condition on depends on what has already been conditioned on, and it's very non-monotonic the way that it works out in a very complicated way. CDAGs, the causal diagrams, are non-unique. That's something that you might not have realized. And model selection for causal inference is super tricky. And the future work that we're going to build on with this is basically once you have the definition of lambda, that minimal control function, even though you don't know it, you can start doing conditional sort of reasoning, saying if mu and tau look like this, what would the corresponding lambda be? And then penalize with respect to how complicated the function is relative to that minimal set. And by doing that, we can show that you can come up with unbiased estimators that can be regularized to an arbitrary degree and successfully screen out noise variables and weak prognostic variables. And so the real, my white whale or whatever is instruments. If it turns out instruments are the tricky one, because you can never know if something is an instrument or if it's a confounder. If you know that it relates to pi, and there is a causal effect, it's going to appear that there's a relationship between that thing and y, because it's going to be moderated through the treatment effect. And so that's really hard to sort of sort out. And that's kind of where the status of this is. Thank you so much for all of your time. And I hope there are a few questions. Anyone?
So one of the last, thank you, that was really nice talk. So I want to go back to one of the last things you just said about the white whale being instruments. So like if you think about some of the like model-driven feature selection, causal inference stuff, like I know you know, a lot of it is this game of how do you, which competing methods are better at including the instruments and others. And a lot of performance benefits basically come from just, can you exclude instruments better than this other algorithm?
Yeah.
And one of the things that to me always kind of undercuts how interested I can remain in that question is that instruments don't arise in practice very often, at least if you're thinking like an econometrician and you're like, I'm going to get tenure on the basis of this instrumental variable I discovered, like they're rare. But is part of what, am I interpreting correctly, that part of what you're saying is like, when we say instrument in this context, something can be an instrument dependent on, I mean, what you were saying, like it's all provisional based on everything else. And
those happen a lot. Conditional instruments happen all over the place.
So even though we know that instruments are rare,
finding an unconditional instrument is super hard. And there's always a footnote in the textbooks when you're doing in the ID chapter that says also you can control on some other variables that will make the ID assumption more plausible. I mean, that's
exactly it. So even though like we know instruments are not that common, it may be that as a practical matter, you have this huge set of possible controls. You can't really.
I mean, like I said, I am in love with, like, I think about hours and hours and hours thinking about this graph. It's really instructive for exactly that reason. Like if you're able, I mean, basically, I didn't talk, the variance calculations are boring, but basically what it boils down to is like you want to control for stuff that are prognostic, and you don't want to control on instruments, right? And so in a model like this, if I knew this, I would condition on X2 and X4. End of story. Like that, and I can prove that that's the best, right? In practice, you don't know what's what, and in fact, you don't even want to have to write down a graph, right? So I just give you all four, and I say, go to town. What do you do? That's what we're trying to build, and it's very challenging, and it might be impossible. Like I think in all generality, this instrument problem is not going to go away. And really, the question is, okay, I'm going to do something super dumb. Carlos can mad me. I'm going to give away a good idea, because even good ideas require years and years of work to turn them into useful. So it doesn't matter. I'm the only one likely to do it. But taking what you just said, one really cool possibility is, let's say that I give you a set of variables, and you say, okay, these are the ones I need, and these are the ones that are instruments. So basically, I said you can, for any given set you're going to condition on, you can then break the remaining up into noise and instruments. Okay. If that's true and you know they're instruments, guess what you could do? You could do an IV regression, right? So basically, there's a version of this where what you do is, as you entertain models, at every step, your variables are either confounders and you condition on them, or they're instruments. You do an IV analysis, you do a regression analysis. Those two things better look alike. If they don't look alike, then one of the two assumptions is wrong. That's the sort of assumption that statistically you can actually make that, because you can make this subject matter assumption that says there's only there's an infinite ways to get it wrong, and there's only one way to get it right, and you can take advantage of that by sort of doing those sorts of parallel regression and IV analysis. That would be super cool, but it requires there's a lot of work to be done to sort of make that operational. But so far that's the only idea that we've had that would, I think, in principle, address the issue, right? And it's problematic because both of them have sampling variability, and so it's a matter of finding the caliber that sort of tells you what size you can do. But so Kang has a paper where they looked at invalid instruments and they applied this idea to. It's a similar logic, but it was just for IV, right? The idea was that any valid set of IVs is going to give the same estimate, and so you can, as long as you have at least some plurality of instruments in your sample, you can get all of the individual estimates, and then whichever one the majority agrees on, right? That's the one. Same idea, right? Like if you're doing this correctly, both types, the IV analysis and the regression analysis should match, and if they match, they're right. So, yeah. Any others? That's too much.
Raise your hand if you're not in religious school. Okay. You go found
Topic confounding. I'm trying to see if there's any sort of other take homes.
If you talk a little bit more about the point that you stated, that you said you didn't really describe, when you're talking about randomization, is less fundamental than control.
Yeah, I mean, yeah. So the example, I always go back to the twin study on that one as sort of like my guiding intuition there, which is that you would like to, scientifically, the way that you do this is you want everything else to be the same. And if everything else is the same, then you know that what was different was the thing. This is the scientific method. Like, that's science. Randomization is just, if you're despairing of the fact that you could never possibly control for anything, you say, oh, well, I'm super clever, I can randomize. And randomization solves the problem on average. And the bitch of that is just that, like, you've only ever got the data that you've got. You don't really get to realize the average in practice. And so, like, if you understand fundamentally what that's doing, randomization is great. It protects you, right? It's like a backstop, but it's not the goal, right? The goal is the ceteris condition. The goal is you want everything to be the same, and that's why I'm philosophically, I'm a big proponent of regression adjustments, like if you can. And what you see, people basically that are worried about doing regression adjustments. I think Friedman, famously was sort of hated it. Was basically like, you could mess things up if you do something dumb, and also you're adding noise if you include a bunch of noise variables, which is all true. But like, if there's something that's really, really important, you can get way better results. So I don't have it in this set of slides, but like, I give a talk where I do a simulation study on the twin example, and I compare what you would get if you did naive randomization versus block randomization versus ex post adjustment. And Yeah, ex post adjustment on the naive randomization, and then ex post adjustment on the block randomization. And ex post adjustment can save your bacon. Like you can get way, way lower variance if you take into account, things that matter. So in that example, I used the birth order as sort of like why you still need to do the randomization. But then I look at a model that did the twin randoms, that did a twin thing that wasn't randomized. That did the twin thing that was randomized, but then you adjust for birth order. It's way better. Because if that thing is mattering, then when you stratify, you're going to get a cancellation when you take the differences, and that's not going to show up in your sampling variance on the estimated of interest. So, it's no oversimplification. Like there's all kinds of details, but I guess mainly I'm overstating my case because I know that students hear over and over and over, randomization is gold standard, RCT is gold standard, RCT is gold standard. It drives me nuts because it discourages people from thinking about the factors that matter. It says, oh, we don't need to think about it, we just need to toss a coin. It leads to really bad cursory science. So maybe you don't have to do all your regression adjustment, and definitely still randomize where you can. But block randomize maybe? Consider adding a couple of regression adjustments after the fact, see what shakes out. So that's, I don't know if that sort of get to the question. All right, thanks everyone.